It's my pleasure to introduce Léonie Papon, that she'll tell us about interface scaling limit for the critical planar Ising model perturbed by a magnetic field. Thank you.
Okay, so hello everyone, and thank you for the invitation, and thanks to the organizers for this event. Maybe we can start by some kind of like general clapping for them, because I'm the last speaker, so we should be the organizer for this afternoon. Okay, so today I'm going to talk about some work on the spin-spin interface scale limit for the planar critical Ising model perturbed by an external magnetic field. So before kind of diving into this problem in particular, let me give you a little bit of background. So some kind of keyword appears in the two previous talks, but I will be maybe a bit more precise. So some background or motivation. So for this problem kind of comes from the question of, okay, how can you understand the scaling limit of interfaces in planar statistical mechanics models? So this question has been studied a lot since the invention of an object called SLE, and I'm kind of going to give you some examples to motivate what is going to come next. So one famous example is that of loop arrays random walk. So in this talk, let me kind of define this model. But so in this talk, I will always work with a domain D of the complex plane, which is bounded, open, simply connected. And so this domain is a continuum domain, and I'm going to approximate this domain by a sequence d delta, where for each delta, d delta is a lattice of mesh size delta, and somehow this d delta converges as delta goes to 0 to my continuum domain T. And you should think of this d delta as either a subset of the square lattice or a subset of the hexagonal lattice, something simple like this. So loop arrays on the mark. This is, so on the square lattice, you have the following picture. So this approximates to domain D. And now you imagine that on the boundary of D, you have two marked boundary points, A and B. Okay, right, I want to take them to the vertex of my grid, sorry. And now you sample a random walk on this lattice, and you erase the loop that you make. So you erase this loop here. Another question that you ask is what happens to this path, so that goes from A to B, as delta goes to 0. So do you have a scaling limit in some appropriate topology? And it has been shown by Schwab, Lohner, and Werner that this converges to a random curve that is called SLE, for Schwab, Lohner evolution, with parameter 2. And this is just a random curve from A to B. And one very important property of SLE2 is that it's conformally invariant, meaning that if I take a conformal map from my domain D to another domain, then the image of the curve under this conformal map will again be SLE2. So this is a first example. Then another famous example that will be important is the Ising model. So now you have you still have your square lattice set. And now on each vertex of the graph, you have a spin that takes value +1 or -1. And this, so for a given spin collection, the probability of such a distribution is proportional to beta times an interaction term. So beta is a strictly positive here, and then this is the Hamiltonian is the nearest neighbor interaction between spins, and you can impose boundary conditions. So if you have your domain D, you can say, okay, I'm imposing all spin on the left to be +1, and all spin on the right to be -1. And on the lattice, deterministically, you create an interface that separates plus and minus spin, so that on the left of the interface, you always have plus spins. And to the right, you always have minus spin. Okay. And then you can ask exactly the same question as here. Namely, what happens when delta goes to 0? And here, the role of the parameter beta enters into play. Namely, when beta is equal to its critical value, so I'm going to call it beta c, then this scaling limit is described again by an SLE curve, but now with parameter 3. And the important thing is that you keep this conformal invariance property. So if you map your SLE3 with a conformal map to another domain, then the image of the curve still has low SLE3. Okay, I could give other examples. So you could look at the interface in the discrete GFF with appropriate boundary condition, or what Yingzhen talked about. So the interface between black and white percolation clusters on the hexagonal lattice. And also in the two cases, you would get some kind of some SLE type object in the limit. And today, what we are going to do is that somehow a few years ago, so already 15 years ago, Markov and Smirnov raised the following question. Namely, so what happens when we perturb this system, these models, in a near critical way? So I'm going to kind of try and explain in a moment what they mean by this. But here, somehow, you have to think that things are critical. So here, you are the critical point. So for those who know the Ising model, where you have the phase transition. And here, you should think of criticality because if you don't erase the loop, in the scaling limit, you see Brownian motion, and this is a conformally invariant object. This is Gaussian and so on. And so what do they mean by perturbing in a near critical way? Is basically perturbing those models, but in a way that you see something non-trivial in the scaling limit. So let me be a bit more concrete. So for loop arrays on the MOOC, what you could do is to add a killing term. So instead of looking at just random walk, you look at the kill random walk. But if you just kill with rate m squared, you won't see anything in the limit. You have to scale the way you are killing the walk, and the killing has to be of order delta square. And if you think about, not about the loop erasure, but just the kill random walk, this is with this scaling that you get kill Brownian motion in the limit. So this is nothing surprising. And for those who know, this is somehow this model of massive loop arrays on the MOOC appears in near critical dimers. then you could play a similar game in the case of the Ising model. But now somehow you have two natural way of perturbing the model. The first one is to be a bit off critical in a thermal way. So instead of being exactly at the critical inverse temperature, go a little bit away. And now the way you to scale the perturbation is according to delta. So for those who know about the Ising model, this is related to how the energy operator of the Ising model scales at criticality. The other natural perturbation in the Ising model that will be of interest today is you still keep the critical temperature. So you still have the same nearest neighbor interaction term, but now you add an external field to the model. So for the moment, it's a constant, but then I can take it more general. And the way you have to scale the field, I will come back to this, is by delta 15/8. And then, okay. And somehow the classic approximation is that the spins want to align with the sign of the external field. But on the other hand, you have this nearest neighbor interaction term, and they want also to align with the neighbor. So you may have a competition between the two. And then you have other examples. So for the GFF that I've mentioned, you could look at the massive GFF. So again, with this delta square, and for percolation, you could look at, so you would look at the property of having an open edge being of order 1/2, which is the critical on the hexagonal lattice, plus delta over 3/4. So this is kind of the idea of perturbing the system in a near critical way. And Markov and Simonov kind of, I would say conjecture that you could still describe the scaling limit of interfaces in the system via some kind of SLE type object, except that you would lose conformal invariance. And the reason why you would lose conformal invariance is because on the lattice, this perturbation, they introduce a finite correlation length, so you can't expect conformal invariance in the scaling limit. But it's not that bad in the sense that this conformal invariance should be replaced by a conformal covariance property. So you would have a parameter that would have to be changed when you go from one domain to another in a conformal way. Okay, and so today, basically, we are going to show what I've just said in the case of the Ising model perturbed by an external field.
So that delta to the 15/8 in front of the...
Yeah, I'm going to come back to this. I will explain where it comes from.
Okay.
I'll come back to this. That's a good question. Are there any other questions while I'm erasing? Well, so the GFF, so instead of taking a usual GFF on your lattice, you take a massive GFF. So, instead of having the Laplacian as an operator, you have Laplacian plus m square. And so in the discrete world or in the continuum, you could think in the continuum. So in the continuum, you impose those minus lambda boundary condition, if you know. And if you do this, when you have no mass, you have SLE4. And you can ask the same, okay? What happens if I have a massive GFF and I impose those minus lambda boundary condition? And it turned out that you can describe in that case what is the interface. And this is a massive version of SLE4. But I can, we can talk about this after if you want. Okay, so let's answer the previous question and discuss the scaling. So remember, now we are looking at the Ising model perturbed by an external field. So we have this. This Hamiltonian, and then our external field, which is scaled by delta 15/8. And I will put a p plus minus here to say that I have those Dobrushin boundary conditions. So plus on the left and minus on the right. And okay, it implicitly depends on delta, which is the main size of my graph, but for the moment I will just ignore this. And so the scaling, so one way of understanding, like one indication for this is a result by Converges. So if you, okay, just for a moment, if you take, so this lambda is a box of size L, and so Euclidean size L, mesh size delta. And if you look at if you take the Ising model with plus boundary condition in this box, and now you look at the spin at the origin, then you can show that you have two constants. So that you are about delta to the power 1/8. Okay. And so this is already an indication that somehow this is the correct scaling, because you should think of it as a discrete integral. So you have a delta square. And now if you want to see something non-trivial, you have to multiply by delta minus 1/8. Because otherwise, this, as delta goes to 0, it will just go to 0. And this gives you delta 15/8. And in fact, and this will be important for later, much more is known about this type of spin correlation function, because somehow here you want to define, roughly speaking, the exponential of this magnetization random variable when you are at criticality. And it has been shown by Shellcack, Ungler, and Isurov, that in fact somehow this is always this scaling in the following sense. So if you have some point, if you have k point in your domain D, that are, so you have to fix some cutoff eta that are at distance at least eta from each other. And from the boundary of the domain. Then what you can show is that if you look at the spin-spin correlation, so it can be any domain, any type of boundary condition. So for example, plus minus plus doesn't really matter. So if you look at the spin correlation of this point, and you multiply by delta to the power minus k/8, so the number of points, then this converges as delta goes to 0. So you have an explicit function, you have a constant and then an explicit function that depends on the domain, and somehow this type of result shows that this is really the correct scaling. Okay.
Magnetic field, the H it doesn't have any length. It doesn't have, it is a scalar. It doesn't have any powers of delta.
Yeah. So H is just a scalar. Then it will be a function of the point. But somehow, I guess what you call length is a delta.
Yeah.
Yeah. If you look at the FK Ising cluster. Okay. So now let's look at the interface. So remember that on the lattice, when I have this Dobrushin boundary condition, kind of deterministically I have an interface. And now what I want to do is to take the limit as delta goes to 0 to this interface. Okay. And so the theorem is somehow the following. So gamma delta is going to be the interface under my Ising model perturbed by an external field when I'm at mesh size delta. And the result is that, well, you do have this interface converges in low to some random curve gamma at delta goes to 0. Okay, I'm not going to make the topology precise. And so I'm going to call this low H. And what can we say about this law? So it's so this law is absolutely continuous with respect to SLE3. So remember, SLE3 is the scaling limit that you get when you have no external field. And then, okay, you have an explicit Radon-Nikodym derivative. So I won't give the expression here because it's a bit long to write, but I'm happy to discuss this if you want afterwards. And then somehow the second part of what Markov-Franzmann conjecture is that this is conformally covariant. So in the following sense. So if you have a conformal map psi from your domain D to your domain D tilde, then psi gamma, so if gamma has this law, then psi gamma has the same law in your image domain with your map point. But now you have to change the external field. So, and you know this H tilde is, what is H tilde? Is this okay if I write here or, okay. This H tilde, so if you have a point X in the domain, you have, okay, somehow the push forward. And now you have a conformal factor. (15/8), where here you again have the same scaling as at the external field here. And okay, if I can explain a bit this, but this is to be expected. So this is this is somehow the result about this interface. So let me discuss a little bit the proof, and then
when you say explicit, how do you mean in terms of what?
In terms that in terms of SLE3. So basically what I'm just saying that I can tell you what, so if you look at something like this, you have a solution A and B, you can do, this is absolutely continuous, so you can do a change of measure. I can tell you what this is.
will be expressed in terms of what?
It will be expressed in terms of those functions in the slit domain. Because, okay, I can do it for any time t, and then somehow you will have this function in the slit domain. And somehow they will be integrated against your external field.
So it corresponds to the massive version.
Yeah. So, and the way, yeah, okay, maybe what I should say is that the term massive in the Markov-Ransmanov paper kind of comes from here, because usually in physics, when you don't have conformal invariance, but when you have a conformal a correlation length, you have a mass, and that's why they call it mass. Yeah, and yes, this is where it comes from.
Here your h is not the constant, so you can start with h that's not constant, also get the similar.
Yeah, that's a good point. I can start with h non-constant as long as it's bounded. So I can take an external field of arbitrary sign, minus, plus, it can vary in the domain, but it has to be bounded.
You don't assume regularity.
Let me remember. Maybe if you want to go everything well, you should assume like continuity or maybe Lipschitz. But not you don't need smooth or something like this. And basically also what I should say is that yeah, no, maybe let me not say this. So the domain D is bounded here, but then via conformal map, via this conformal change, you can define the law in unbounded domain, provided it comes from a nice domain so that your field has this form. I don't know if I'm super clear.
So in particular, this absolute continuity property, even like also holds in infinite domains.
Well, basically it holds if your external field is inherited from a bounded domain. Maybe okay, as far as I know, because maybe it's true for any kind of
If I take a constant h of the upper plane.
That I don't know. That I don't know.
And this PHDAB, this is, you have a definition directly in the continuum.
No, basically I obtained it from scaling limit.
And then what does that mean if you start with the h depending continuously, like you have this h tilde depends continuously on x?
Yeah.
You can say h is constant, but h tilde is a smooth function of x. What is it? How do you define that ph tilde?
Well, yeah, okay, I see what you mean. Basically, it's just because, so you have this expression here, and then you know that this is conformally invariant. So you know that if you map the domain, you get SLE3. And then you can say, okay, here I have an explicit expression. I can just look at what happens when I do this conformal map. And then this defines the law of the image curve in your new domain via this Radon-Nikodym derivative. So yeah, maybe there is one that I get in this from scaling limit, and then the other one I get it in the continuum when working with the Radon-Nikodym derivative here. Yeah, if you want. But it's not like yeah, okay. Yeah, okay. It's more like I understood the question as, okay, SLE, you have some kind of nice characterization and stuff like this. Here, I don't have that. I just have this, yeah, I have this definition. Okay. So let me kind of give some idea for the proof. So actually, the idea is very simple. So yeah, still a bit here. No, I don't. Sorry. So if you remember, so okay, I've just erased it. So if you remember, so you have this you have the law of your Ising model, perturbed by an external field. And then when you see this somehow at the discrete level, it's very easy to see that you have a Radon-Nikodym derivative with respect to the unperturbed Ising model. So if you and this is just given by the normalization constant, and then the exponential of h delta 15/8 sigma. But now on your lattice, the interface is measurable with respect to the spin. So this change of measure kind of descends on the change of measure on the interface at the lattice level. So what I mean by this is that you can write that on the lattice, the interface can be obtained as via this change of measure. And then you take the conditional expectation under the critical measure of your perturbation given the interface. Okay? And somehow, if you, okay, so this is just an observation for the moment. And if you've already worked a little bit with scale limits of interface, usually, you have a two-step strategy. So first you show tightness, and then you characterize the subsequential limit that you obtain via tightness. But here you have this object, which is a Radon-Nikodym derivative. So, and you know that, okay, the law of gamma delta under this measure is tight because it converges to SRE3. So if you want to show tightness somehow, you just have to show that this Radon-Nikodym derivative is uniformly bounded in some LP space as delta goes to 0. And then you have tightness. And then if you want to characterize the law, which may be a bit more complicated usually, you can simply show that this random variable, again, converges in a suitable sense. And basically, this is just how the proof works. And one key point for this, and I won't say much more because then it's somehow some technical work maybe, is that you can use the definition of gamma, so of the interface, and together with with the Markov property, to kind of write this Radon-Nikodym derivative in a way that makes taking limits a bit easier. And yeah, maybe I should say here, instead of conditioning on the whole interface, I could stop at after some time or some step, and I could do exactly the same and get somehow the Radon-Nikodym derivative when you stop the curve after some time. Okay, and so somehow the way the proof work is, okay, so you can rewrite this Radon-Nikodym derivative as, so you still have this normalization constant, and then what you do is that you decompose this random variable given this curve. So what happened is that okay, I'm going to use this to do just a little cartoon. So if you have your interface, on the left, So you will have an Ising model with minus boundary condition. Okay. When you condition on the interface, and on the right you will have an Ising model with plus boundary condition. So this is how and those two models conditionally on gamma, they are independent. But you also have in this conditional expectation, okay, you can split what happens to the left, what happens to the right. But when you condition on gamma, you also learn about the spins directly near the interface. So when you look at this conditional expectation, in fact, you get a product of three terms. So I'm going to call omega L what happens on the left, and omega R what happens to the right, and those are random domains. They depend on my interface. Sigma x. I know that for the x on the right. Then you have the same thing, but with minus boundary condition. Sorry, this is on the left. Same thing with minus boundary condition on the right. And then you have the contribution of the interface. And what happens for the interface? So, well, this is relatively easy. The spins who are on the left have a minus, so have a plus, sorry. So I'm going to call this BL gamma. So this is the number of spins on the left on the interface. And then you have a contribution from the minus for those who are on the right. Okay, so you have those three terms. And now you want to take the limit for this. So these two terms are not so problematic because you can kind of expand the exponential, and if you expand the exponential, you will get the k-point spin correlation in the expectation by just expanding in Taylor series. So this kind of problem had been looked by in a slightly different setting by Christophe Gardon, Charles Newman, and Federico Camia. But here, where you have to be a bit careful is that when you condition on gamma, you are working in a domain that in the limit is going to become rough because your SLE is fractal. So here, somehow for those two terms, the main technical work lies in dealing with this rough boundary when you take the scaling limit. And then you have this term that is kind of the magnetization of the interface. And you have to do something with it because it could be potentially problematic. But here, everything is okay because if you think about it, this is in between minus the total number of vertices along the curve and plus the total number of vertices along the curve. Okay? So, and what you know is that, and this gamma here, remember, this comes from the Radon-Nikodym derivative. So this gamma has the critical law. So at the law of the interface for critical Ising. Okay, and what you know is that under this p plus minus delta, the limit of gamma is SLE3. And the other dimension of SLE3 is 11/8. Okay. So somehow, so this is not a proof. This is an heuristic argument. You have to work a bit more, but somehow it indicates that if you look at the total number of vertex along gamma, it's going to scale like delta minus 1/8. And okay, maybe you will have some correction. But this tells you that this term is just going to vanish in the limits because this delta 15/8 is going to kill this divergence of delta the minus 1/8. So yeah, so and basically if you if you do all those steps correctly, then you get the result.
So the same argument allows you to go a bit away from the boundary from.
Yeah, exactly. Because somehow here, you will have a divergence of order delta minus 1/8. So let's say, okay, in the continuum, maybe it's easier. In the continuum, the divergence comes from, so you typically you will have a conformal radius term that scale like minus 1/8. But because your boundary is rough, but not too rough, this will be still integrable near the boundary. And so somehow you have to adapt what happened in the continuum to the discrete world. And this is related to arm exponent of SLE3. Okay. Are there any other questions? Okay. So now I'm just maybe in the remaining 15 minutes, what I want to discuss is, okay, I've kind of told you what happened when you have this exact scaling for the external field. So when you have this delta 15/8, but you could ask, okay, what happens if I don't take the near critical scaling? Can I see something interesting, or is there nothing appearing because a priori it's not so clear? So I'm just going to tell you what happened in.
Where's the 15/8 so important? Because here it was dominating the other power. So you could have changed this 15/8 to 11. So
that's true. But
where is that needed?
Remember when I say, okay, I have those two conditional expectation on the left and on the right, and I'm expanding the exponential. When I expand the exponential, I get I expand the exponential, so I get k factorial, and then I get this sigma x to the power k, and then I get the delta 15/to the power k. And I have an expectation, sorry, I switch the expectation here. I take the sum out, so I have this delta 15/8 k, and then the sum, and then the expectation of the product sigma x1, sigma xk. Okay? And somehow, if I want to take the scaling limit of this, I really need this delta 15/8. So it comes from the result of Sheldrake, Ongler, and Ising that I mentioned. So that's true. For the magnetization of the curve, this delta 15/8 is not so important, but for the convergence of the conditional expectation, it is. Okay, so the first result that I'm going to illustrate when you are not net critical. So in this is in the case of a small external field. So in which sense? So you take a function g that goes from r plus to r plus, and this function g goes to 0 when delta goes to 0. Okay. And now you take the Ising model with external field. And you still take h delta 15/8, but now you multiply by g delta. So you're going to 0 faster than delta 15/8. And you ask the same question. So you have Dobrushin boundary condition, you have an interface. What happens to the interface when you take the scaling limit? And it turns out that somehow, in that case, this field is so small that its scaling limit, you forget that you were perturbed by an external field, and you converges to FLE3 exactly as when you have no external field. And the reason why is because you can look again at the Radon-Nikodym derivative that I've just shown you because you exactly have the same formula. And now if you take the scaling limit, you will see that this Radon-Nikodym derivative converges to 1. So you have FLX3. And now, the other result is, okay, this is for when the field is small, but now what happens when the field is large? So, and here, okay, h is a constant, but it could be a continuous function bounded. But for this result, I really need h to be a constant. So let's say h is positive, like this. And now I have a function f. But now f goes to infinity as delta goes to 0. And I'm not assuming any kind of rate. And I'm taking as an external field, I'm taking h delta 15/8. And then I'm multiplying by this half delta. So I'm going to 0 slower than before. And then, okay, I want to look at what happens to the scaling limit of the interface. And it turned out that somehow the field is so big that it's super hard for the model to have a long path of minus spins. So in that case, the interface is just in the limit going to stick to the boundary where you impose minus boundary condition. And here I should say this is because this h is strictly positive, but if you switch the sign, you will stick to the plus boundary. This is okay. And maybe I should say, so for here I've used the Radon-Nikodym derivative, but for this proposition, it's not that you can't, but I don't know how to do it with the Radon-Nikodym derivative. So the proof strategy is a bit different. It's a bit more probabilistic maybe in nature. So maybe let me kind of say roughly why you have this. So in a simplified setting, maybe. So let's say you have a box and you have those boundary conditions. In any, it doesn't matter, but to make drawings, it's easier. And somehow you start your curve here, and you want to end here. And what you can try to understand is, okay, what is the probability that the curve exits the eta neighborhood for arbitrary eta of the minus boundary arc, okay? But now you can divide this small rectangle into two, okay? And basically reaching distance eta from the minus boundary is implied by having a crossing here with plus and minus, okay? But now the nice thing is that this event takes place a little bit away from the boundary and in a way that is macroscopic in the sense that it is independent of delta. And this means that you can use some type of mixing type argument to say that up to multiplication by a constant, the probability of this event is roughly the probability of the same event, but with plus boundary condition. And now if you do this, for Ising, it's really nice because you can use the Edwards-Sokal coupling, and you can kind of try and understand this event using the Edwards-Sokal coupling and looking at events that take place in your FK Ising model, for those who know the Edwards-Sokal coupling. And so typically, what you want to show is that in your Edwards-Sokal coupling, with probability tending to 0, you will have tending to 1, sorry, you will have a path of plus spins that crosses this rectangle. And here, this is the, okay, remember that you have an external field. So in this Edwards-Sokal coupling, you also have a ghost vertex, and clusters can be attached to the ghost vertex. And if they are attached to the ghost, they have sign plus, okay? And okay, I won't be super precise, but basically the reason why you have this thing is that if you are a cluster, the probability that, okay, given the configuration you are attached to the ghost, I'm going to make a mistake. It's given, oh yeah, that's true. By the, so the size of the cluster times your external field. I've done that. And this is the hyperbolic tangent. And somehow, so this is still not quite the result, but somehow you can show that you have this event and that the clusters that of the FK Ising clusters that contributes to this event, there you can choose them so that they all have size of order delta, so of order delta minus 15/8, which is somehow the typical size of an FK Ising cluster, so that you kill this one, but because you still have this F delta that goes to infinity, the probability of being attached to the ghost goes to 1. And somehow this gives you a path of plus spins that crosses this rectangle, and that prevents your interface from going there, because you can't have minus crossing here. And this is somehow how you can show this type of result. So I think this is everything I had to say. Thank you for your attention, and don't hesitate if you have questions.
Thank you. Question or comments?
Yes, maybe I have one. So in the article you mentioned by Camille Derman, I think they also construct the whole limit of the field, I mean of the magnetization field. And should this one be singular with respect to the physical one, while the interface is absolutely continuous, or is it?
No, the magnetization field is absolutely continuous.
Okay. But this does not imply that the interface is.
I think in that case it implies, because you have exponential moments. If you do a bit of work, but I guess
So
basically
is it an alternate proof of what you say, or
no,
no?
No, it's not an alternate proof. Also because this is not an alternate proof, and they construct the field as a distribution. So I probably, what I do, you wouldn't be able to do it with the way they construct the field, because I'm testing against the world domain, basically. So you have to, whereas they can only test against functions that are smooth and compactly supported.
So what you say, if I'm a beginner in this area, so I don't really know how it works. But what you say is that you can't extract the law of this massive SLD curve from their construction. That's right.
So I think you could extract it if you know that. Okay, it could also be the case that in the continuum, your critical magnetization field can be coupled with an SLE3 in the same way as the GFF is coupled with an SLE4, and in that case, you could extract the law of the so this PDH blah blah blah. You could extract it in the continuum if you had a coupling in the continuum, but this coupling has not been constructed, so you can't do it that way.
You don't remember about the SLE, massive SLE3 coming from the massive Ising model?
So for the moment, it hasn't been constructed.
That the E3 one?
So no. What they did is for, as far as I know, what they did is for massive loop arrays on the MOOC. So they look at the scaling limit of the massive loop arrays on the MOOC, and they show that it converges to some type of massive SLE2. And you can define it as taking square root. You can define it via the driving function or via some characterization property using a martingale observable. But for the Ising model, when you perturb the beta, it hasn't been constructed.
But if you have to guess if that's
So
constructed, would that be any way?
So what I can say is that I think some kind of folklore thing that has been tried is that you can take Smirnov fermionic observable. So the observable that is used to show convergence to SLE3. You can look at it when you have a perturbation of beta, and instead of having a discrete holomorphic function, you have a massive discrete holomorphic function in some way. And so you can try and play the same game, right? You take the scaling limit, and then you try and characterize the curve by saying that, okay, if I have an observable which is the solution of this boundary value problem, so a massive version of the critical one, it characterizes a Uniqlo one curve. But okay, I think you have technical problems to take the scaling limit, and also it's super unclear that this observable do characterize in the limit a low-one curve, because somehow all the Ito calculus you want to do is become really messy when you are in a non-critical setting. So this is one approach that has been okay. It's a bit of folklore, but I think that has been tried. The other thing you could try is to look at this Radon-Nikodym derivative thing, but here somehow you would need cancellation to take place because you don't have at all the same scaling. If you remember, you have a delta instead of a delta 15/8, and this is somehow less nice to take scaling with. But okay, I should also say this is somehow related to the fact that probably you can't construct the energy field of the critical Ising model as a distribution in the continuum.
Your question? If not, let's thank the speaker again. And thank you all for coming to this event.